un minuto, que quiero dejar esto bien acomodado.
¿Voy presentando?
Ya, dale.
Okay. Hello everyone. Thank you for joining to the hard morning session. We have an amazing dinner last night. It was really good, everything. We had a good time. Very nice. Thank you.
Good music.
The music was great.
The music was great, yes. So, I will now start. If you see the schedule, Carl Esposito will should be the speaker, but he asked me to kindly change my lecture with his, because he knew in advance that he will not be able to make it that early. And actually, it was a great decision because we remained discussing things until kind of late. So I will start. And I was checking the presentation this morning and trying to recompile it, but for some reason I had this crazy LaTeX thing that sometimes happens, and you can solve, but not in 5 minutes. And my presentation, which is an adapted version of this one, it got, let's say, could not compile. I don't know why. So I said, okay, there is not much difference. So there are some references here, like the mathematics department of the British Columbia University, which is not anymore my affiliation, and the date is 2016. So, but there is not much advance that I have done in the last 2 years on this, because I've been working on something else. And I will try to speak about that in the other lecture. Not sure if I will have enough time, but anyways, I wanted to tell you my story or my connection with the quantum and cognition. ¿No está?
No. ¿Me lo prestas un
Sí.
poquito?
Ah, falta el USB. So, this is in the style of what Professor Soto Andrade, the guy with the beard, yesterday was explaining. It's on, off, on. Okay. This works, and this works. So, but it's a little, slightly more formal than what he did. So that's why it's called Towards a Quantum Theory of Cognition, because this is not necessarily a formal theory yet. It's just some formal indications. So I start with a bit of context that refer to the idea of conditions of possible experience, and that's very, very important. I will talk about that in the next lecture, because this is very foundational thing. When conditions of possible experience, when satisfied, they indicate that the data may have, when not satisfied, they indicate that the data cannot have resulted from an actual observation. So what can be observed, or what can be deduced from the data that was observed, are these conditions of possible experience. And this is clearly not my style of redaction. It's George Boole's style, so that's how he expressed this idea of conditions of possible experience. So I'm trying to go to a very foundational topic in science, but from the cognitive perspective. So foundations of, I say, cognitive science. And it is related, and not anymore to my PhD, but to a group of researchers that I'm trying to build here in Santiago, connected with the Belgian researchers, with Dirk Ayers and his group mainly. So this is the point. So we are trying to ask foundational questions. It's a little, sometimes the steps we do are a little large. So I'm trying to maintain very humble, very lower to foundational things, because people think I will present and say quantum cognition, also the mind is a quantum object, is a quantum computer. No, this is only languages to describe certain phenomena. It's just like very, very on the surface of epistemology. No further than that. So we will talk about the classical notion of experience, the notion of experience as expressed by Boole, and then what happens with these conditions of possible experience in cognition. And then the idea of introducing quantum theory as a language to express the data that emerge from the conditions of possible experience in cognition. It's a proposal. And then if I have time, I will make a quantum cognitive model, like a quantum-like model of concept conjunction and negation. So data obtained in experiments of conjunctions and negations. So, as I said, George Boole introduced this notion of possible experience in his book, and the idea is to constrain the relative frequencies of an observational procedure. So, we have talked a lot about that already, so I will not remain for long in this part. So, the idea is to constrain the relative frequencies of an observational procedure. And the basic example is the urn with red and wooden balls. So balls can be red or another color, whatever, and can be wooden or another color. So you will not expect, for example, that the probability to extract a red and wooden ball will be larger than the probability to get a red ball. It's impossible, because there are no more, so the likelihood cannot be larger. So these are the constraints that represent the logic of what you are doing. The first one says that there cannot be more red and wooden balls than red, or no more red and wooden than wooden. And the other constraints the way in which, if you have a set-like representation of this, it cannot happen that the addition of those probabilities. So that's the probability that either red or wooden cannot be larger than 1, basically. The exclusive order probability. Okay, so these are basic constraints, and this is, as for those that have more quantum foundation flavor, this is pretty much the Titowski-Politov approach to Veloz inequalities. When you do this for more experiments, you obtain something like CHSH and stuff like that. But then you see numbers, you see data. Let's see. Probability to get a red ball 0.7, probability to get a wooden ball 0.42, and probability to get a red and wooden ball 0.1. That looks pretty much like real data, like something that can happen. You will not expect that that is not a possible experience, and actually the violation is very low. Just an inequality, in the second inequality is violated by 0.02, which is not that much, but still. You can put larger numbers like 0.5 for mu-v, and still these numbers, just by like basic impression, you will not question that that is real data. In principle, no one has these inequalities in their minds. You see numbers and they make sense or not. In principle, then you can put them in equations and see if they actually make sense or not. But as a simple understanding, like in a basic, as I tried to say, like in a basic, very basic impression, these numbers should not look as weird, so weird, like, oh, they cannot have, like, it's not that as if I put 1.1 for a probability. You immediately get an impression that that's not possible. You see what I mean? So there are different degrees of belief of what is possible. And that's where I'm trying to go with this talk, that in cognition, what it is possible goes beyond to what actually is possible in macroscopic reality. So, the mathematics of conditions of possible experience, I explained that the existence of a classical probabilistic representation, and they will always be satisfied if experiments are performed on a single sample. If you have all the experiments performed on a single sample, there is no way you can escape from the conditions of possible experience. So they relate, they can only be violated when measurements are somehow destructive or transformative of your sample. So, more of the mathematics, this can be deduced for any logical system, for any system with any experiments with different number of outcomes. I'm just talking about 2 outcomes, 2 experiments, but you can expand it to very different things, to all the possible, let's say, measurement descriptions. And these are some of the languages that have been used to construct these ideas. correlation politics, probabilistic logic, linear programming, category theory, recently by the Oxford group, and so on. So they are all equivalent in the end. And there are certain mathematical interests from the purely formal perspective on representing what can be satisfied, what bounds one can obtain, or whether you can optimize certain problems in one language or another. Typical mathematical problems you have when you have a new language. So, it's very, now back to the foundations, it's very interesting that the conditions of possible experience bridge logic with probability and with experimentation. So, they are basically at the very core of any theory, of any scientific theory. It's very hard to escape from these questions. So, in cognitive science, they have assumed that these conditions hold. Like, no question, no discussion about it. Let's build cognitive theories without even questioning whether this holds or not. So if you see the development of artificial intelligence or decision making, economics, novel artificial intelligence, database, the theory of databases and so forth, they are, and a large and bold, etc., they are all assuming implicitly that these conditions will hold. So it's because it works for like physical sciences, then it would work for cognitive sciences. It's just a basic, bold, and uncareful assumption. The problem is that there is a body of experimental evidence that challenges the validity of these conditions in cognition. So the first example is the violation of the Earn inequalities we obtain, when instead of considering Earns, we consider basic categories. And we talk about the membership of a certain instance to this category. So we try to think in terms of sets, and what we obtain are not the logical structures of a set. So we force people, in experiments, you force people to think as if categories would be sets, and then what you obtain is that they do not think in terms of sets. They think in terms of other things. So from the fuzzy logical perspective, we would expect that an exemplar, xk, that has probability mu k, and then you evaluate on the concept. So this is the membership of exemplar, let's say, instance, which can be anything. It can be this. Is this a beautiful thing? Or is this a useful thing? So these are the categories: beautiful thing, useful thing, and this is the instance. So K is the instance, A and B are the concepts. So you will see that if concepts will be categories, will be sets, they will behave this way, right? So the problem is that you find strong, what they call overextensions, which are the inversion of this in experimental data. From the 80s, 70s on, this has been running from the 60s already. So the basic example that this is data, real data gathered by experiments and so on, with lots of preparation. You prepare the person, you explain what is said, you make all the efforts for them to think in set-like terms, and then what you get when you combine these concepts, furniture and household appliances, then you estimate the membership of ashtray, vacuum cleaner, coffee table, and so on concerning these concepts, and what you get is something like this. So I will explain briefly. If you get two concepts, of course, one and then one instance, two concepts and one instance, you will have that one of them is the minimum, the other will be the maximum, regardless of which of them was the minimum and the maximum. So I just plot the minimum and the maximum. I don't say A and B, this is not relevant. We're just thinking about structure. Then the dotted line is the average of the minimum and the maximum, and then the com is the actual combination, the A and B thing. So what you see is that we did a statistical analysis of this, and what you see is that the average plot fits much better the data than the minimum on the maximum in terms of fitting the curve, and as well in correlation, and many other statistical indicators show that the average is a much better first approximation than the minimum, which will be, or something below the minimum, and any function below the minimum, which will be what you expect from classical logics or from set-like thinking. But there are two red points there that are marking something very remarkable. That is that the combination of concepts sometimes goes even beyond both concepts. So you have something that, so the ball is more likely to be red and wooden than being red and then being wooden. It's completely out of mind from a set-like perspective. It's like the intersection is larger than the former sets. Doesn't make any sense. But this is typical psychological data. And this is very similar to the, for example, Professor Soto yesterday was mentioning the Linda experiment, the conjunction fallacy. This is also the same. Feminist and bank teller is more likely than bank teller. But in this case, it's even more likely than feminist as well. So this actually, the model that he presented yesterday cannot, the quantum model he presented yesterday cannot represent these points. This has been proven in 2016 or something. We were discussing about that. It's the ARTS group proved that. So we need to do some other models. There's still quantum, but it's just this is pretty much like back to the quantum, just to make a little teaser. This is a double slit-like situation. You see? So you have that the combination gives you for via interference processes. I mean, as an explanatory mechanism only, not saying that concepts are quantum objects, but as an explanatory mechanism, you can use double slit-like structures to explain this type of data. So that's pretty much the idea of quantum cognition. So there are many other examples of non-classical cognitive data, many others, but I will mention, if you go on Wikipedia, this was part of my new version of the talk. If you go to Wikipedia, the cognitive theories are called rational and biased. So we are rational beings and we have some biases sometimes because we are not perfect. The only problem, because this started following the tradition of Aristotle, right? We are rational. We are rational because we want to be, and that's how we feel good. Being humans, we want to be like God and so on, so we are rational. But sometimes we make mistakes. So because we are not gods, we are some imperfect creatures. So let's identify scientifically our biases. What are our biases? And that was the research program of Tversky and the famous Daniel Kahneman that won the Nobel Prize. Think Slow, Think Fast, book, very known everywhere. So they were the guys that formalized this research program and got the Nobel Prize in economics for the theory they developed on top of that. So they need to identify bias. But now, current research shows that we have more than 200 biases of different sorts. So if you want to look for a first principle theory and you have to put 200 band-aids to it, I don't think it's a nice approach to say we have this structure, but there are 200 cases in which they will not work, and we discover more every week that they are separable, different cases. You cannot reduce them to classes of biases. There is no way. They just different ways in which we deviate from rationality. So maybe it's it makes you feel that you might better question the first principles, whether we are rational or not, rather than assume blindly rationality and put hundreds of biases as fixed heuristic mechanisms that will fail, that we would fail on rationality because of that. So, more examples. Borderline contradiction. John is tall and not tall. Sometimes it's true. We handle, and this is something very nice to say, I like this part, we think in terms of contradictions. We have no problem, we do not halt, we do not stop our life when we have a contradiction in our mind. We live with contradictions all the time. We can handle them in a certain way. Of course, they are contradictory and it is not easy to think of these things, but they have been also from the Greeks on. The liar paradox is a thing that is true and false and so on, and it is there. It's a mental, it's a possible mental structure, it's a possible cognitive experience, a contradiction. So, it's not in reality, but in our minds we can handle that. It's part of our realm, the realm of our thoughts. So the conjunction fallacy was looked upon already. Order effects which deviate from this law, the probability that the order doesn't affect. But of course, all these things, as I said, and also uncertainty about irrelevant variables matter. So if B is an irrelevant variable, you have this. Even if it's irrelevant, if it is relevant, you go very far from this. And even if it is completely irrelevant for your situation, this can also happen. So we are here we can think of mechanisms to explain all this, and many people have tried, but you have to find a class of explanations for one thing and then a class of explanations for another thing, and then you fall again in the problem of putting band-aids to the theory. Because there is no principle theory to explain why we have to explain it this way here and in that way there. You see, the economics work a lot on that. Anyways, so going back to the structure of these things, we know already that they are not sets and they do not combine as sets combine. So we cannot think in terms of these things. So now let's call it semantic entity. This thing, the cognitive entity, semantic entity, can be an idea, a category, a decision, and like just trying to start from scratch. And we can identify three crucial features that characterize the seemingly strange behavior. Vagueness, fuzzy boundaries. For category is very easy to see, and its fuzzy set theory is based on that. We cannot say what is a large number. We have we know that 0 is not a large number, and most of us believe that the Avogadro number is large. But what in between? How is the truth assignment or the probability of truth of saying a number X is a large number? That's the basic fuzzy set theory paper by Sadek in 1969, I think. Then another very important feature is contextuality. The way in which we think of concepts depend on the entire situation where the concept is elicited or thought of. And the other is non-compositionality. These three things are discussed in different ways in pragmatics, for example, in the theory of linguistics and philosophy of language, philosophy of mind. These are discussions that go around for decades, and they all pretty much arrive to these conclusions, but with different words, different ways. And non-composition is a big problem that started with Vrije, that whether we can obtain the truth by decomposing, like Cartesian, let's say, manner, decomposing in parts and so on. Can we then recombine and get the truth? And of course, for music, for poetry, for art in general, we know that things are very non-compositional. Like we cannot just combine, like separate two things and we have half art here and half art there. It doesn't work that way. Things acquire meaning when they get in their whole situation, not in their parts. So this is these three features actually also remind you the structure of quantum systems. Vagueness. I think I have this. Yeah, they have been largely no formal tools have proven to be satisfactory to combine these three features to provide a theory for cognitive systems that handle these three weird features. So, but these features are fundamental features of quantum theory, and I show the double split situation, the entanglement. So just to show that there is a connection. And then we can make this bold assumption. This is vagueness. We can talk about vagueness in terms of state superposition. There is no concrete state. There is a vague state which is superposed and it doesn't even exist in our physical reality. But it is part of the theory. So we can say the same for concepts. They can exist in superposed states, which will never be thought, will never be spoken out. It will never be an outcome of a cognitive process. But the processing, the mental processing, might perhaps work with superposed conceptual states. You see, so that's the idea of quantum condition. And then the context we can, well, the context is a word in quantum theory already, but we can become measurement-induced collapse. And the non-compositionality, there is no foundational principle for it, but there are mechanisms to obtain that in quantum theory. We have mechanisms to obtain that. So then the idea, back, it's an analogy only, as I said, quantum particles and concepts. This is just a formal analogy to establish. So then we work with the tools of quantum theory to represent cognitive systems and nothing else. We could call it Hilbert cognition, Hilbert-based cognition. I like it better, but I don't put names here. Names are already given. So the notion of possible experience strongly depends on the properties of the observation process. And this has been discussed in large depth and beautifully by Pitofsky, a paper by Pitofsky called On the Conditions of Possible Experience and the Quantum Puzzle. This is a beautiful paper by Pitofsky, where he explained what is the interplay between possible experience and the features of the observational process. It's really nice. So, now we consider this analogy. The state of a quantum system, the meaning of a concept, is dependent. A concept, remember, this was the semantic entity, so just whatever. Dependent on the measurement, dependent on the context performed on it, in which it is elicited. When concepts are combined, its state can be non-compositional, its meaning can be non-compositional. So it's just following this idea because of the structural reasons. And then this is a little bit of advertisement. What these people, the people who work on this do, they try to identify quantum structure and they try to create quantum-inspired or Hilbert space, let's say, better models for cognitive situations. But there is no position, nothing, not even to talk about whether the brain is a quantum system or whether we are quantum machines and so on. That is not, it's not that the question. I think it's important to discuss that, but the fact that we don't have an answer or we are agnostic about that doesn't mean this can be done. This cannot be done. This can be done without even talking about that. Just for the sake of understanding, if we can build at least a formal theory from basic principles, or whether there is a basic structure that we can rely on to build a theory for cognitive systems, like let's say ontology and epistemology of cognitive systems. So if we have the formal tools, it will be much easier. So we just try to stretch the power of quantum theory to see how much we can get of, well, Hilbert space, probability, Born rule, and so on. So, but the interesting now, the key steps, the basic idea is that concepts exist in a state rather than being container of instantiations. So, concepts are not sets, concepts are not urns. They exist in a state. It's a very different thing. It's at least more similar to what Karl Sposik presented in the quantum logic course, these generalized urns. So the balls do not have a color or a shape or like a material before the measurement process. They do not have a color. In classical physics, balls are there and they have a color. So in cognitive systems, we, like inverse like thinking, like just looking at the data, we can obtain or deduce that they actually don't have a color all the time. Anyways. And entities are observing a particular state that is observation dependent, and then you can, what I explained before. So now you can start applying the notion of collapse, observer effect, non-symmetry, and so on. And then when you combine concepts, you have let's say, the possibility or you are forced to introduce this type of things if you want to work in quantum terms. So I will present this, and I guess I might close with this, yes. So consider this experimental situation of estimating the membership weight. How much is this instance, banana, with respect to the concepts fruits, vegetal, under conjunction, fruit and vegetable. And then we can identify two kinds of reasonings. And this is part of the research we did in 2009 and so on, from 2009 on. banana can be an exemplar of the concept fruit and vegetable all together as a new concept, this third concept, or can be thought as an exemplar of fruit and an exemplar of vegetable separately. So there are two ways of reasoning about conjunction in cognition, in the reality. But the thing is that we have to assume if they become two different ways, if we conceive the concept fruit and vegetable as structurally different than fruit and vegetable, logically speaking. So if we open up the possibility that fruit and vegetable is not the combination, the logical, the set-like combination of these concepts, then we have to assume there is a third entity that can also be built, perhaps can be constructed, but it's not just the intersection of two sets. That's the point. Of course, if we think of concepts as states, as entities in a state, and this is another concept, it has a different state, different states, not necessarily the same. So, and then I will make the drawing here just to make it more clear. Notice that when you consider the entire concept as one single entity, the combined concept, you only need one banana to make your evaluation. When you think in logical terms, you have a truth table, and then you need two bananas, one for fruit and one for vegetable, two events. So this is what we call, this is the mode of thought, let's say, the way of reasoning that we model in Hilbert space. And so, and actually the concepts, because they exist in states, then we make this concept the superposition state of both concepts. So the state gets, there is a superposition state. So we build it that way. And this is the logical mode of thought. That is, we can model it using the tensor product. Actually, it said you can obtain all classical probabilities using tensor product description. This is, I don't know if it's well known in physics, but it's very trivial because of independence and so on. And entanglement can help you to model, how to say, the dependence. When you have, like, when the probability is not the product, but you have a different values because there is dependence between the systems. Anyways. So how do you do this model? Each concept exists in a different state, and a membership operator is introduced for the exemplar banana, in this case. So you apply the Born rule, and you obtain the probabilities that banana is a fruit, banana is a vegetable. And then the first mode of thought, where you combine the two concepts, you create a new emergent state, which is the average. Simply, it can be, of course, a weighted average and so on and so forth, but for simplicity, we only take the average value. And then you take Born rule to estimate the probability, and you get that the average is first approximation, and then you have the interference term, as in the double slit situation. And the second mode, in the classical, is a combination, is a compositional state. In this case, I only show the tensor product of the states, but you can use entangled states as well. And you can derive all the classical conditions of possible experience in this setting, applying the measurement operator and so on. This is very, and this will be the measurement. You can also apply entangled measurements and so on, but this is part of another, like it goes beyond, it's a little technical, but very interesting. And then the superposition of modes of thought, that will be the most general model. Superpose the one Hilbert state mode of thought with the tensor product. So we go to this truncated thought space where only two modes of thought are allowed. First mode of thought, second mode of thought. And you get that this is the state. So AB1 is the first, and this is the, remember, the tensor product or the tensor basis state. And you have this coefficient, that this is just a model, a coefficient of how quantum or how rational you think. So then we obtain the probabilities and so on, and then we start representing data of conjunction, disjunctions. So we test, can we assume that conditions of possible experience of this type apply in cognition? Because this gives you new conditions of possible experience. What can be the outcome of data? Right? This is, not every number is possible here. There are certain, many constraints. So we tried with this experiment for conjunction and negation of concepts. So we tried the estimation of being a fruit, not fruit, vegetable, not vegetable, fruit and vegetable, fruit, not vegetable, not vegetable, fruit, not vegetable. So we tested the Morgan laws, whether the Morgan laws hold or not, right? So here we got what this should be 0 because of the what is this, the marginal probability. So we tested here the marginal probability, but the idea is to test how the Morgan laws look in real cognitive data, whether how do we deviate from them. And then many concepts, many states, and we did our statistical analysis. So the data is stable enough so we can derive conclusions. So if we look at this obvious classical condition for individual concepts, so the probability of A plus the probability of not A has to add up to 1. So we tested this estimator, and then we tested confidence intervals, so where people, when the deviation, where it goes. And the numbers were very, very close to 0. Remember that the maximal value of this will be 1 or -1, right? Depending on the value. If if they would say 0 for A, 0 for not A, this will be 1. And if they would say 1 for A, 1 for -A, it will be -1. So the range where these numbers move is between -1 and 1. But you get numbers pretty close to 0. Decently, like relatively close to 0. Not 0.1, 0.3. So for certain numbers you go 0.1, but you don't go 0.3 or stuff like that, which would be like a large deviation. There's no large deviations from the basic idea. So one concept in a certain way is thought, one concept and its negation is thought as a set. But when you go to the combination, the other estimators that I show you here, how they deviate with respect to the combination, to the law of marginal probabilities, then you go to very large deviations. The law of marginal probability deviates very, very great, like largely. And actually all the numbers, if you look, are statistically very close because these are confidence intervals. 95% of confidence that the deviation will go there. So these are the intervals. So in most cases, because we have no variables to try, what is a fruit, what are the variables behind fruit or vegetable, we don't know. But we see a tendency to go close to 0.4, minus 0.4. So the non-classical deviation for this experiment, which we tested different concepts, it goes more or less to the same place. So then we do the model, and this is fixed. The model I will not tell you details, already explained. And then this is conjunction data, the later conjunction data, the Hampton, the one I presented in the beginning, and this is the conjunction and negation data. So what I did here is to try the different parameters of the model, in particular the parameter of emergent thought, how much the contribution of the Hilbert space model is needed, and how much of the contribution of the tensor product model is needed to balance, to get a better fit of the data. And in both cases, you get that with 0.8 emergent, so 0.8 non-rational or double slit like, is the best approximation of what data tells you. So in this, the journalistic conclusion of this is that we are 70% irrational or double slit like, or 80%, around 70 and 80% irrational all the time. And only 20% of our thoughts are rational in daily life examples. So the emergent mode of thought, which means concepts when combined they acquire double slit-like structure, is very dominant. And if you take I'm working now with the conjunction fallacy data because there is a lot of experiments, more than 200 experiments carried out, and more than 35 experiments that have decent enough data so I can model that. And we find the same, actually. It's something very strange that in psychological experiments there is a very clear tendency to be irrational in a certain particular manner. It's something. I'm not saying that this means we are quantum waves. It's just that irrationality or the deviations from conditions of possible experience are quite, let's say, sharp. They are not randomly distributed. So conclusions. Yeah, I said that. And the interesting thing is, shall we think of new possible conditions of possible experience for cognition? Or we need to start with this, thinking about these structures. Thank you. Okay, there is some time for questions. Thank you, Tomas. Yes, please. We need the microphone, sorry. Let's make it a little.
So I ask you a question that the students, when I teach quantum mechanics to philosophers, always ask me. Is there a need, a formal need for using complex numbers? I mean, why should this be a Hilbert space and cannot just it be a vector space on a different field like real and okay.
Yes. Thank you. The complex numbers are needed to obtain the interference values that we have in the data, to model the data. Yes. If you stick to real numbers, you have a new set of conditions of possible experience, which is producing.
You have evidence that it is necessary.
Yes.
Okay.
That's what we. I mean, if not, certain data cannot be modeled. So maybe you can use another structure that doesn't mean complex numbers, and you will get better. But if you work with this structure, you will need the complex numbers to get the power necessary to make the fits of the data. So yeah, that's it.
Yeah, thank you. My question is serious. In the review paper on the quantum cognition, previously, Graham Bismayer said there is no fundamental reason to use quantum mechanics.
No.
But this is an analogy, and if we use quantum mechanics to explain, he explained some concept called deviation or something like that. That is the reason to use quantum mechanics. But do you overcome this analogical stance?
So let me confirm, is the question, because they talk about these cognitive illusions, right? These were introduced by Kahneman, Tversky, these guys. And your question is if we overcome the...
Using quantum mechanics is just analogy.
Okay. From my point of view, yeah, for me, I don't like to call it quantum mechanics. I like to call it Hilbert space probabilistic structures. And actually, it's even worse now because we have strong evidence, like new evidence, not so new, but around that time, that Hilbert space structures are really too tight to handle every possible cognitive situation. So you need an even more general probabilistic structure. I know that Krennikov work on positive value measure operators, which are slight generalization, but still you need even more. That doesn't mean that you need like an open function, whatever. It's just you see structural reasons to go further and further, and that's what I like. I stick to quantum-based Hilbert space mathematics because there's a lot to do. There are many tools, but we know already that in principle that will not be enough. So, question?
Well, it's again a related question. So what you see is that you have those probabilities in connection which don't follow Kolmogorov set theory, etc. So you need something else.
Yes.
Now, is it something else quantum theory or not? It's absolutely unclear to me.
Yes.
I discussed with some Krennikov also. If I see, for instance, the way I deduce Borg's rules from Gleason theorem, etc., actually the structure is really rigid. You have these modalities, you see this fixed number is, for instance, it would be equivalent to any question, the number of mutually exclusive answers is fixed, is always the same.
Yes.
Which is true in quantum mechanics because it's a dimension of the universe space, which is generally wrong in connection. That is, if you ask different question, you will also get a different number of answers. It's not a fixed number. So it seems to me that what allows me to deduce quantum mechanics is much more rigid, because it's physics in some sense, so it's much more rigid than what happens in cognition. So I fully agree that you need something beyond the Kolmogorov and sets theories, but what is it? I don't know, by the way.
Let me comment on that, because in the beginning I had, because the structural analogy that was presented here between the vagueness, non-confusionality, contextuality, and so on, it points like as a very good candidate. Quantum theory would be a very good candidate. Why? There is no clear reason why. It's just one feels good about it. But the real reason why, I think, is because a well-structured theory. So that's why, and there is a famous searching. If you lose your keys at night, you know that thing. If you lose your keys at night, the only place where you can look is where there is a light bulb around. So even though your keys might not be there, that's where you can see. So trying to see the structure of cognitive systems is the same. You know you are in the Kolmogorovian light bulb, and you already know the keys are not there. So you have to go to the next light bulb, and what's the next light bulb? It's one of them is quantum theory.
For instance, saying that superposition is fuzziness, I think is wrong in our approach. If you consider that linear superposition is fuzzy, in our approach is totally wrong. Actually, linear superposition is a certainty in another context. So,
yes.
so you see, it will not really fit with something fuzzy.
Excuse me, this makes sense, and this is why also it's good to make this analogy in this sense. Because context is again another, its context, remember, in this model plays the role of the instance. So the instance that you are testing the concept with is the context. So if you are in a certain mental state, it's called mental state, for fruit and vegetable, which will tell you that banana shows some superposition, then perhaps apple will be your eigenvalue, you see? So it makes sense. And I mean,
except that it's very rigid in physics.
Yeah, yes, no, for reasons of combination, combining more concepts and having more complex situations, but at least certain questions make sense. So that's why this is still not, I'm not saying that I have the solution at all, but I think that it makes sense to think in these terms and also can be helpful for education. It has some other values, excuse me.
Thank you. Interesting talk. I have a couple problems. It seems to me that your model is based on observations, an observation being able to determine a context from which follows meaning.
Yeah.
I guess that's the problem that I have. It loses value completely when you move into a social system. So it's a rather common experience that even amongst quantum scientists, that no one can agree on what the meaning of the quantum is, even though it is the most predictive of all physical sciences. No one seems to agree on exactly what it means, and therefore people want to replace it with a different theory. So I think that's where the problem is that you can't move from this system to a social system. So you can't pick up conflict, you can't pick up disagreement between observations. So you and I have to agree on what the observation is. And if we don't agree, like, for example, the red tablecloth, We can probably agree that that's a red tablecloth and it has no banana on it. But if we're trying to say whether capitalism or communism is good or bad, we'll immediately run into conflict.
Yeah. Thank you. That question is very interesting. And this is, again, the way to dodge this question is to say that this theory, these cognitive foundations that I'm presenting here, assume from scratch that the best knowledge you can have is statistical. So you do not represent, this is just a method to make it understandable, but we are not claiming to know how people think or what the meaning of people, what is meaning actually. It's just a tool that you use to make your explanatory mechanism understandable. But this is only people thinking, having whatever model in their mind and answering a certain question. And then you take the statistics of that, and that's what you can model. So it's not an explanatory mechanism. I mean, we could discuss further on that, of course. I have my own ideas and so on, but at the level of what I'm explaining here, the social measurements you can do, again, you give me the data and I will tell you how to model it. But there is no explanatory mechanism yet, so far. So this is actually why I'm not entirely satisfied with this development. Because it only models, fits data and tells you, oh, we are irrational. But it doesn't tell you any explanatory mechanism, no capacity to predict so far. The best prediction I can give, and the only prediction I can give is to say, okay, people will deviate from rationality this amount, but towards where, I cannot tell you. I can only know that a percentage of people will behave in a very weird manner and so on, sort of like Pareto law in a way. That 80% of people will be rational in this way, 20% will be rational, and no more than that. So it's what I think that if really a quantum-like theory of cognition will be developed, these are the questions that have to be answered first. So yes. Any other question? I don't know why I thought you would ask.
Professor Soto.
Yeah, there's one. Professor. So last question, and then we go on a short coffee break.
Well, thank you. Among several questions, I was wondering about the relationship between what you suggested now and the fitting model of the density model I talked about yesterday. But there might be some fancy relation which is relevant that you could understand in terms of metaphor theory. So the idea would be that a cognitive subject is in a superposition of states, and one state is one metaphorization, one state is a different one.
Yes.
So we have the state as containment metaphor, and we have the density or fitting metaphor. And so we are in a mixed state. And eventually this collapses according to the context.
Yes.
So this would be one approach, and there is a related question, is I think Carlos would react maybe when you describe what a concept is as a semantical entity, is very much close to the description of a living system. So we may eventually conjecture that to model concept is as difficult as modeling living systems. And this might be related to the first one.
Thank you. I think that both questions deserve a longer discussion. It's absolutely, I agree with that. And I have many things to say about the relationship between living systems and cognitive systems and so on. But I will just contribute with a little thought, with a small thing that is there's something that Liane Gabora with Leading Heights worked on Liane Gabora's PhD thesis, which is the question of the emergence of an evolutionary process. So what are the conditions that you need so an evolutionary process begins? And not out of other evolutionary processes, so a new structurally different evolutionary process. And which evolutionary processes will be your candidates? Life is one, language is another, and of course cognition is another. So this or social, globalization or something like that. So the emergence of societies. So these are out of certain rules emerged a new thing that starts evolving on its own, and before that it didn't exist. And that is the completely non-Darwinian, because Darwin only speaks about what happens when the evolutionary process is already running, but not how a new evolutionary process begins. So that's I think it's related to that, but it's really for delaying a lot the conference, staying very long. So we thank you, our speaker. Thank you.